Welcome to The Explainer. Today we're going to crack open one of chemistry's most elegant concepts. We're talking about a hidden force, a kind of secret superhighway running inside certain molecules that gives them some pretty remarkable properties.
So let's just jump right in with a puzzle that has, believe me, stumped chemistry students for a long time. You look at a molecule on paper, right? You do all the calculations, and everything tells you it should be kind of reactive, maybe a little unstable. But then, in the real world, it's incredibly sturdy. So what's the deal? Where is it getting this hidden strength from?
Well, the answer to this whole stability puzzle isn't some kind of external force acting on it. Nope, it's actually found deep inside the molecule's own architecture. A very special arrangement of its bonds that basically changes all the rules of the game. And here it is. This specific pattern is what we call a conjugated system. Just think of it like this: a chain of alternating single and double bonds. Single, double, single, double. That's it. This simple repeating pattern is the absolute key that unlocks this entire phenomenon of extra stability. Okay, so what's so special about this arrangement? Why does alternating single and double bonds matter so much? To really get a feel for it, let's step away from the hardcore chemistry for just a second and use an analogy I think you'll like: a highway system. See, in most molecules, certain electrons, we call them pi electrons, are what we describe as localized. That just means they're pretty much stuck in one place, shared between only two atoms. You can imagine them like cars that are totally confined to these short, local side streets, unable to really go anywhere. But in a conjugated system, that alternating pattern of bonds creates this amazing continuous path. And all of a sudden, those pi electrons are delocalized. They're not stuck anymore. They can just zoom across multiple atoms along this brand new molecular superhighway. And this newfound freedom of movement, well, it changes absolutely everything.
Now, this electron superhighway isn't just some cool analogy we made up. It actually has a formal name, and it's one of the most fundamental concepts in all of organic chemistry. It's called the resonance effect.
So officially, the resonance effect is a permanent property of a molecule. It's where the sharing or delocalization of pi electrons over that whole conjugated system creates areas of positive and negative charge. And most importantly, it adds a huge amount of stability to the molecule.
So you might be wondering, how do chemists even draw something like this? I mean, the electrons are always moving, so you can't just draw one static picture. What they do is they draw all the possible states, or resonance structures, showing all the places the electrons could be at any given moment. And they use these little curved arrows to map out their journey along that highway.
Okay, but here is the most crucial point, the one that trips a lot of people up. None of those individual drawings are actually real. The molecule doesn't, flip-flop between them. The real molecule exists as something called a resonance hybrid, a single, stable, blended average of all those possibilities all happening at the same time. And this is where that incredible stability comes from. By spreading the electrons out over a bigger area, the molecule gets to lower its overall energy. It just gets to relax. The real resonance hybrid is always more stable. It's at a lower energy state than any of the single structures we could ever draw on paper. We call this resonance stabilization. Now, this effect isn't a one-size-fits-all deal. It actually comes in two distinct flavors, and it all depends on the different chemical groups that are attached to that electron highway. These groups can either be pushing electrons onto the highway or pulling them off. Seriously, just think of these groups as on-ramps and off-ramps. A pushing group acts like an on-ramp. It donates electrons, adding more traffic to the superhighway and increasing the electron density. A pulling group, you guessed it, is like an off-ramp. It withdraws electrons, pulling traffic off and reducing the electron density in the system. So first, let's talk about the groups that show the positive resonance effect, or plus R. These are our electron pushers. These groups, like the amino group you see in aniline, usually have these extra lone pairs of electrons that they are more than happy to donate right into that conjugated system, making it much more rich with electron density. And on the flip side, you have groups with a negative resonance effect, or negative R. These are the electron pullers. Groups like the nitro group in nitrobenzene are what we call electron withdrawing. They literally pull electron density out of that highway and towards themselves, which makes the system as a whole more electron poor. Now, at this point, you might be thinking, hang on a second. I've heard about another effect that pulls electrons, and you're probably thinking about the inductive effect. You're not wrong. So let's take a quick second to clarify the really crucial difference between these two.
So here's the breakdown. The resonance effect, as we know, operates through the pi bonds. That's our electron superhighway. The inductive effect, on the other hand, works through the sigma bonds, which are kind of like the basic framework connecting every single atom. It's a much weaker short-range pull that fades out with distance. So you could say resonance is the highway system, while the inductive effect is more like a local tug-of-war.
Okay, so we've defined the effect, we've explored its two flavors, and we've even distinguished it from its cousin, the inductive effect. But why does any of this matter outside of a chemistry textbook? Why is this one of the most important concepts you can possibly learn?
Because, and this is the key, this is not just abstract theory. The resonance effect is an incredibly powerful predictive tool. It explains the legendary stability of molecules like benzene. It tells us exactly where a molecule is electron-rich or electron-poor, which lets us predict where chemical reactions are most likely to happen. It is literally the roadmap for chemists to build new molecules. And that brings us to one last thought to leave you with. We use all these drawings, these resonance structures, as a kind of crutch to help our brains understand a much deeper reality. But if the true molecule is this blended hybrid of all of them happening at once, what does it actually look like? It's a pretty powerful reminder that the true, beautiful complexity of the molecular world exists way beyond any single picture we could ever possibly put on a screen.